Good morning, ma'am.
Am I audible to all of you?
Yes, ma'am.
Yes, ma'am.
Why only yes, madam? One yes, madam.
Yes, ma'am. Good
Am
morning.
I audible to you?
Yes, ma'am.
Yes,
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. So just in 2 minutes, let me know what we were discussing earlier. We discussed what is corrosion. We discussed the electrochemistry part to understand corrosion. And in corrosion, we have seen why metals undergo corrosion. Then there are two theories which are important. That is wet theory or electrochemical theory of corrosion, and the other one is dry corrosion or direct chemical attack theory. Now, according to direct chemical attack theory, it is the product of corrosion which will either protect the metal or it will allow the metal to undergo corrosion to a great extent, and that is given by the Pilling-Bedworth rule, which says that the thickness of the oxide film formed, if the ratio of oxide film formed to the metal consumed is greater than 1, then it is protective, non-porous, and therefore protective in nature. Okay, then we saw wet theory of corrosion, in which we saw that there are three reasons why an anodic and cathodic areas should form. The first reason is when you connect two dissimilar metals, anodic cathodic area will form. If you are having crest and trough, anodic cathodic areas will form. If you are having an impurity which is very noble, then rest of the surface of metal will become anodic and the noble impurity will become cathodic. If you are having impurity in a metal which is very active like zinc and magnesium, then we see that a small area, impurity area will act as anode. The moment a small area starts behaving like anode, a pit is formed or localized attack takes place, and an intense localized attack leads to embrittlement of the material. Then we saw different types of corrosion in which we saw biological or bacterial, microbial corrosion, then stress corrosion, then pitting corrosion, then waterline corrosion, and intergranular corrosion, right? Then we were looking into design and material selection so that corrosion will not take place. So the next part is material selection. So we see that you should use one should use purest type of material metal so that corrosion does not take place. Then for reducing the conditions for reducing conditions, nickel and copper alloys are often used. For oxidizing conditions, means like where the oxidizing conditions are there, chromium based alloys should be used because the oxide of chromium formed will protect the surface and will not allow further oxidation to take place. Okay. Then for extremely powerful oxidizing conditions, titanium and its alloy are commonly used. Then mnemonic alloys, that is nickel, chromium, and molybdenum, are used in gas turbines, very resistant to hot gases. So for hot gases, mnemonic alloys are used. Use of proper metal for a particular environment should be there. So each metal shows minimum corrosion at a specific pH, and corrosion can be controlled by adjusting the pH of solution or the acidity or alkalinity of the environment. So like you can optimize the pH range in which you can use um, the metal. Then there are protective coatings. Now, protective coatings are like many coatings are there. One is metallic coating. Now, you know that stainless steel, it is galvanized. So, galvanization is coating of zinc layer on the steel metal. So, zinc is always a sacrificial material which sacrifices itself. Even if there is a scratch, the zinc part will undergo oxidation, and that is how galvanized sheets are protected from corrosion. Then other type of metallic coatings, they are used to protect metal by separating from corrosive environment and serving as anode. Coating applied through electroplating, roll bonding, or hot dipping. Okay, so roll bonding means just like you laminate your originals between two sheets of plastic, the metal is also metal cladding, and that is done by putting the metal between two thin sheets of sacrificial material, or uh, which will sacrifice itself. Or hot dipping, like certain metals which liquefy at a lower temperature, they are liquefied and your metal to be protected is dipped into that hot melt. Then you get metal hot dipping. Then might have several layers or several serve as barriers. So that may serve as a barrier, or that may that may be having several layers, or it may be what you say, maybe working by sacrificing itself. So that is how the one metal may protect another. Inorganic coatings are ceramic and glass, or glass lined steel vessels are generally some in some applications they are used. So you can line it by glass and ceramic. Organic coatings are organic polymers like paints and varnishes are generally used. Then design, material and design selection. So material we saw. Now coming to design, weld rather than rivet containers to reduce crevice corrosion. So I don't know whether diagrams are there. Well, now you see what is a rivet, like when you have two such metal plates placed over each other, then rivet is something which is having such kind of mouth and a smaller part here. So that part is put here and then it is hammered from the upper end or the lower end. So when it goes like something like this with these things. So that is termed as rivet. Okay. So the rivet is generally this metal is somewhat uh, like this will be a different metal than the sheet, and that is why anodic cathodic areas may form at this rivets. So instead of rivet, it says that if you are having two sheets, you you should use some weld material which will put and like fill this gap as well as this gap from the lower side, so that the portion becomes gradual like this and this portion becomes gradual like this. Now the moment this edge part, there is no such corners, then accumulation of moisture, dust don't take place at this part, and the corrosion is stopped or reduced. So use a galvanically similar metal for the entire structure. So a single metal, if it is used, it is always better. Avoid dissimilar metal that can cause galvanic corrosion. For galvanically dissimilar metals are bolted together, separate them with a non-metallic gasket or washer. So when if you are nut bolting this part by dissimilar metal, then put a washer here. There is a nice diagram in SS Dara's book. You should definitely read from that. So if you put a washer here, that will avoid the contact of two dissimilar metal. Avoid excessive stress and stress concentration in corrosive environments to prevent stress corrosion and cracking. So, especially when using susceptible materials such as stainless steel and um, brass. So this is the design. It says that if you are having such a structure, dust and moisture or water may accumulate at these corners. So a structure without corners is always preferred, like this here. Okay. So it should not be, that's why it is termed as a poor structure. Whereas here, the water, if it falls here, will trickle down, and that is why it will not remain stagnant here. So this is termed as better structure, and this is termed as the best one if it is held horizontal, vertical like this. Then coming to different type of protection. So the first one is design and material selection. Second one is protective coatings, the paints and all we saw, metal coatings and organic coatings. Then the third one is cathodic and anodic protection. Now there are two types of cathodic protection. The first type is use of sacrificial anode. Okay, so use of sacrificial anode, where you use uh, metal which is more active than the metal to be protected, and the other one is impressed current cathodic protection. Okay, so sacrificial anode is like you are having a metal like magnesium which is very active compared, like now you want to, like this is either under the soil or under the seawater. Then this is your tank which is to be protected. So you connect it with an insulated copper wire. This is very important, that this wire should be insulated. And this part, if it is connected to material like Mg, this automatically, this Fe becomes cathode and this becomes anode. And when this becomes cathode and this becomes anode, oxidation will take place in this and reduction will take place here, and this part is protected because oxidation will not take place at this, and that is how you get the structure gets protected. So magnesium and zinc is contact with steel, current flows from the more active anode to the steel cathode current. Like you see, when metal will go in dissolution like this, electrons are retained here. When the electrons are retained here, electrons will flow in this direction. Okay, so this will be always rich in electrons, and hence oxidation will not take place at the Fe metal, and the tank will be protected. Then sacrificial anode continued. Then iron tank is turned into cathode and active metal is used as the anode. Magnesium is often used as sacrificial anode in soil to protect small electrically isolated structures such as underground storage tanks and well coated pipelines. Uh, that is the reaction. Magnesium 2 plus 2 electrons undergoes reduction at minus 2.37 volt, and iron undergoes reduction at the potential of minus 0.44 volt. Okay, so zinc is often used in marine environment, and that is how, instead of magnesium, if it is seawater, then zinc will be used. If it is soil, then magnesium will be used for uh, protection. So, what is the basic concept of cathodic protection? The basic concept of cathodic protection is you render your structure to be protected as a cathode. So, at cathode, if you make it work as a cathode, it will be always reduction taking place, and therefore the structure will be protected. Then another type of cathodic protection is, one was sacrificial anode, the second one is impressed current cathodic protection. So impressed current, so you have an AC rectifier. Now this AC rectifier, the negative terminal of this is connected to a tank or a pipeline running under the ground. Excuse me. Okay, so impressed current cathodic protection is you apply a AC rectifier, and the tank or the pipeline to be protected is rendered cathodic because it is connected to the negative terminal of the rectifier. So externally you are applying certain potential so that the tank will be protected, and the anode part or a metal which is quite passive or noble is connected here, like your platinum or any other noble metal, less precious, can be kept here. Now this less precious or not very, because the process should not be very expensive also, but a noble metal is kept, which is rendered anode. So this anode, this is like this is connected to the positive terminal. So this noble metal is rendered anode, and this requires a very careful monitoring, that it should be like maintained for this particular values, the potential values, and it will be protected by not having any oxidation reaction at the tank, because this will act as cathode, so reduction only will be taking place here, or there won't be any reaction, just zero current condition. So sufficient DC current is given to the underground tank, so that negative terminal connected to the structure to be protected and positive terminal to inert anode. So the anode is generally inert, like your platinum, silicon, then graphite and so on. So the application is protection of buried water and oil pipeline, marine structures, ship hulls, water tanks can be carried out. So, what is the difference between a sacrificial anode cathodic protection and impressed current cathodic protection? So, it is seen that in sacrificial anode cathodic protection, after few years, you have to replace the block of your active metal, magnesium or zinc, because that goes into the into the soil. So external power supply is not required here, whereas external power supply is required here. Number two is periodic replacement of the sacrificial anode is there. Number two, here there is no replacement required. But here you see this is suitable when current requirement and resistivity of electrolyte is low. This is suitable when the current requirement and resistivity of the electrolyte is low. Then this is suitable when the current requirement and resistivity of the electrolyte is low. This is suitable when the current requirement and resistivity of electrolyte is low. In both the cases, it is the same thing. So this is not a differentiating point. Rather, uh, here you are using a noble metal, and which is rendered, and you need a DC power supply. Economical method for short-term protection, suited for large structure and long-term operation. Investment is high, investment is low here. So apart from this, one important factor is this requires proper monitoring. Okay, proper monitoring of this battery and all should be there, whereas this, once you put it, you can forget for at least 5-10 years, and after that you put another block of the sacrificial metal. So these are some of the differences. Then coming to an important thing, that is anodic protection. Now what is anodic protection? You render a metal anodic and still it is protected. How can it possible? Is it possible? Yes, anyone? Do you understand the meaning of anodic protection? Word anodic protection. The structure to be protected is rendered anodic. You make it behave like an anode and still it is protected. Is it possible?
Sacrificial protection can be done.
No, sacrificial anode cathodic protection we have already seen. We started with the first type, that is cathodic protection, in which we saw sacrificial anode and impressed current cathodic protection. So these are the cathodic protection part. Now what we are doing? We are rendering the metal tank uh, anodic and still it is protected. So the important part is uh, oxidation will take place. So when you render any metal as anode, oxidation will take place. But the oxidation product forms such a coherent, non-porous film on the metal surface that the surface of metal is protected thoroughly and there is no more corrosion, no matter sulfuric acid is kept there or like this part is the oxide film formed. So, especially for holding the corrosive compounds, anodic protection or metals which show active passive behavior are used. Okay, so metals which show active passive behavior can be protected by anodic protection. So, which are the metals that show active passive behavior? It is nickel, iron, titanium, chromium, aluminum, and their alloys. They show active passive behavior. So, this active passive behavior is important, otherwise, you can't go for anodic protection. So, what is anodic protection? A technique to control corrosion of metals by making it anode of an electrochemical cell and controlling the electrode potential in a zone where metal is passive. Okay, so that is anodic protection. So, for understanding what is anodic protection, so the metals which can show um, active passive behavior. So in one environment, it is active, and in the other environment or potential values, it becomes passive. So if you remember, we have seen a Porbec's diagram. My graph will also not be good. In Porbec's diagram, we saw that there is a pH, and here is the potential. Okay, so we saw that around such something like this was seen. Such type of four-peaks diagram was seen. So before we discuss the anodic protection, we will see the four-peaks diagram. Now this is the four-peaks diagram for iron system. Now what is here? Here is the potential value plotted versus pH. Okay, this is a more magnified figure. Now what is saying, if your iron metal is held at this potential value, iron metal है जिसको इस potential पे रखा है. So if you render it cathodic, that is, you connect the negative terminal of impressed current or you attach it to zinc or magnesium, it will start behaving as cathode. So this becomes cathodic protection. Here it is in the zone of corrosion. But once you make it apply a positive potential and make it anodic, it leads to formation of like it gets passivated because of formation of an oxide film which is protecting the underneath layer. So in this region, that is, by increasing the potential to some extent, you are converting you are passivating it. So anodic passivation or anodic protection, it is termed, this green zone. And such kind of Porbec's diagram, now this is the iron system, can be there only for these active passive behavior showing metals like nickel, titanium, aluminum, iron, chromium. Okay, so if your potential, like see, this is the X point, if you make it anodic, it goes into anodic protection, that is, it forms a protective layer on the surface of metal so that the underneath layer are protected. Or you change the pH of this. Suppose if the pH of this is 5 here, or here in this diagram you can see it is 6 here. If you change the pH, you are moving from the corrosion zone. This is the corrosion zone. This small part is also a corrosion zone. So you are moving from a corrosion zone to neutralization, that is pH 7 or 8 like this. But that also to some extent only you can change the pH. So this iron system is studied intensively for such type of phenomena, that what is the potential and effect of pH on the iron, and how it shows, whether it shows corrosive behavior, corrosion takes place at what potential, and that concept is used in anodic protection. So in anodic protection, you use a potentiostat which has three terminals, and this device um, is connected to the tank to be protected. If controlled anodic current is applied, metal gets passivated and the rate of metal dissolution decreases. The potentiostat shifts the corrosion potential into passive potential so that the corrosion of metal is stopped. It is based on the formation of protective film on the metals by externally applied anodic current. Potential range depends upon the relationship between the metal and the environment. Now, this is the diagram for anodic protection. This is a potentiostat, this one. Okay, now this potentiostat has three terminals. Suppose if this is your uh, working electrode, one is the working electrode, the tank to be protected. So the tank is your working electrode here. One will be your auxiliary electrode, or it is also termed as counter electrode, or CE. And one will be your reference electrode like calomel electrode, silver chloride electrode, and so on. Okay, so here one is the iron tank, strong corrodant or electrolyte. This is the electrolyte present, which is say an acid kept in an iron tank. Then tank is made anode number 2. So this is the working electrode, or the terminal of this is connected to this potentiostat. Then you will have, this is 6 is a voltmeter which will measure the potential, which measures potential between okay, if 6 is the voltmeter here, then this should be your reference electrode, because the potential of your working electrode, the tank, is maintained with reference to the reference electrode, and this must be the counter electrode. So the unwanted current or whatever current is generated, that will be carried through the counter electrode, and you will have the ammeter here to measure the current flowing through this pole into here. So 7 is the ammeter. That means if this is ammeter, okay, then this is the counter electrode. So current flows through the counter electrode. So the three electrode system. One is the working electrode. So the potential of this working electrode or the tank is maintained with respect to the reference electrode. So the central one is the reference electrode, and the potential applied is measured with this voltmeter, which is between these two, and there is an ammeter to measure the current flowing through the counter electrode, and that is how you render it anodic. Now, what is important, that the metal should remain passive in a good potential range. That is, what is the potential range? The potential range over which the metal is passive should be wider. That is, at least 50 millivolts range should be there in which it remains passive. अगर यहाँ shift होते हैं तो corrosion होगा, आगे चले जाएंगे तो corrosion होगा. So this region of potential in which it is passive should be wider. Okay, at least 50 millivolts region पे वो passivated रहना चाहिए, so that you apply exactly that potential in between this to protect the structure. So current density needed to start the protection should be as low as possible. Lower the passive current needed to maintain the protection, the lesser will be the operating cost of the anodic protection. Then application. Extremely corrosive environments such as high acidity or corrosive chemicals handling, reactors, heat exchangers, and transportation vessels for corrosive solutions may be prepared or may be protected by anodic protection. Then anodic protection is most preferred choice for the protection of chemical process equipments. Chemical students should keep in mind. So distinguishing feature of anodic and cathodic protection. So it is applicable only to those metals which show active passive behavior. Here it can be applied to all metals. It has a very high installation cost. The installation cost of cathodic protection is low. A potentiostat is TAT. A potentiostat is required, which is an electronic gadget. Here you need only a sacrificial anode or DC power supply. Mm, So you don't need an expensive uh, device like potentiostat. Then directly measures corrosion protection rate. Here it is a complex process, does not indicate corrosion rate. Okay. Then coming to cost of corrosion, engineering design is incomplete without knowledge of corrosion. So you have to know the cost of corrosion. Then coming to the next part, so this completes your protection. Then coming to fuel cell. Now what are fuel cell? What are fuel cells? A fuel cell is an electrochemical conversion device. It produces electricity from fuel. Uh, Fuel is oxidized by an oxidant, and there are two compartments, one for the fuel and the other for the oxidant, and in between will be your electrolyte, and two electrodes will be there. So mostly what we see is there is no combustion reaction taking place, but due to the electrochemical or chemical reaction taking place, you will find that the current will flow or electrons will migrate from one electrode to the other, and that is how the fuel cell will work without combustion and production of carbon dioxide. Okay, so a fuel cell battery or fuel cell is the common type of fuel cell is hydrogen as a fuel and oxygen as an oxidizer, such type of fuel cell. Now here we see a better structure. Hydrogen oxygen fuel cell, here is the structure. Okay, now here is the fuel inlet. The fuel goes here. You have a permeable platinum doped graphite here, palladium doped graphite here. So different metals are doped into your anode and the cathode. So this is the anode compartment and this is the cathode compartment. So here the reaction that takes place is twice H2 gives formation of 4H plus, and your 4H plus form, 4 electrons will move from the anode to the cathode. Here will be your load, and here oxygen is supplied, or air inlet. Like oxygen from air may be used or pure oxygen. Now the astronauts who carry such hydrogen oxygen fuel cell, they use oxygen, but here we can just study with air also. So this oxygen with this 4H plus leads to formation of pure water molecule, and this water is used by the astronauts for drinking purpose also. So this particular plant is where you see the reaction taking place. At the anode, this is 25% KOH. It is not written here, percent KOH. Okay, so the electrolyte is 25% KOH. Now, for different operating conditions at very high temperature, very low temperature, this electrolyte will be changing, because this electrolyte should not freeze and should continue this thing. Then more research is on having increasing the efficiency of fuel cell. If you change the catalyst which is used here, platinum or palladium, which is impregnated in graphite. Okay, so if you use a cheaper one instead of platinum and palladium, can it give you same efficiency? That is around 85% is the efficiency. So the power conversion is 85%. So this particular thing here, you see the cathode reaction is O2 plus 4H plus giving you 4 electrons, that is forming H2O. So the final reaction is this giving you H2O, pure water for drinking. So the advantages are it is a noise free power plant, emission less, so eco-friendly. There is no emission, only product of the chemical reaction taking place is you are getting electricity and pure water from this if you use O2 as an oxidizer gas and H2 as the fuel. Okay, then the electrolyte is 25% KOH, which remains here. So fuel cell system are environmentally sustainable. High conversion efficiency is there around 85%. PPT is little what incomplete. Extremely low emission. Extremely low emission means what? There is no emission of carbon dioxide and all. CO or CO2, it is totally absent. There is no carbon used in the fuel in hydrogen oxygen fuel cell. Noiseless operation and standalone power plant has no moving parts on it. Then availability to use at any location, sizing can be done, so less transmission and distribution losses, no requirement of cooling towers and conventional plants, less space required to as compared to the conventional plant, standalone power plant, noise-free power plant. All are these. The main disadvantage of fuel cell are high initial cost and low service life. Okay, so these are some of the advantages, same as we had discussed. Then some numericals. These numericals are based on your Nernst equation. So the first numerical, can you see the numerical?
Yes,
Yes,
ma'am.
ma'am.
Okay. So this is a numerical. I'll just tell you, you have solved
Ma'am, the
this
top
one.
part is little bit not visible. Topmost part.
Consider the electrochemical cell Fe2 plus zero point 0.1 molar is the concentration of this, and then you are having cadmium 0.001 molar cadmium. Cadmium ion concentration is 0.001 molar cadmium. So it's not a concentration cell, but it is an electrode concentration cell, or you can say the electrolyte concentration. The electrolyte concentration is also different. So you see the you can write the numerical, and such type of numerical may be asked, rather it was asked in some exam, that is why has been put. So cadmium has an E naught of minus 0.4, whereas iron has an E naught of minus 0.44. So we expect that this is a um, greater negative value, so oxidation will take place at a greater negative value. So before we go, whether oxidation is taking place here, is it really a left-hand electrode acting as anode? We will verify by calculating the E half values for each of them. So E half for cadmium is calculated, comes out to be minus 0.48, and E half for your this particular electrode comes out to be minus 0.46. So looking into the potential values under such concentration conditions, we say that oxidation is taking place at the cadmium electrode and reduction taking place at the iron. So what all representation is shown to you is not the true representation, rather, or this is the cathode part and this is the anode part that you have to understand. So cathode minus anode, and then calculate the equilibrium constant, which you can definitely do if you get it in the examination. So log K comes out to be this value. So taking anti-log of this value will give you the equilibrium constant K value. Things are clear? Okay. So the next one is this is another cell in which copper and hydrogen electrodes are there. The concentration of copper and H plus is given to you as it. So here we see that what is the cell potential, the complete cell potential is asked, and you can calculate the complete cell potential from this value. So one is copper part. So copper under this conditions of concentration comes out to be, it's not 0.34, but with the concentration of Cu2 plus ions it is zero point 0.1. It comes out to be plus 0.31 volt, and that for H plus with concentration of 0.01 molar comes out to be minus 0.118 volts. So based on these potential values, this is positive, this is negative. So this is acting as an anode with oxidation taking place here, and that will be E right minus E left, or E cathode minus E anode will be 0.31 minus 0.118 minus minus plus, so it becomes 0.428 volt. Okay, then this is a concentration cell. Now this is an amalgam concentration cell in which the concentration of zinc in mercury is different. So C1 is 2 grams of zinc in 100 grams of mercury, and C2 is 1 gram of zinc in 100 gram of mercury. In between is the, say, consider that it is a zinc sulfate solution or zinc chloride solution. Zn2 plus aqueous is there. So which electrode or which part of the H-shaped tube will act as anode and which will act as cathode? So we see that if you consider reduction at one of the place and oxidation, so reduction to take place at C2 and oxidation at C1, and you substitute your E cell value minus E naught will be same, so that cancels out. So negative 0.0591 by 2 log C2 by C1, this is coming out to be positive. That if the cell potential is coming out to be positive, what you have considered that C2 is the reduction um, half cell, then C2 is here, the reduction is taking place, and here oxidation is taking place with a cell potential of positive 0.0089 volts. Things are clear? Okay. The next one is, like, you have a hydrogen electrode with different pressure of hydrogen gas. So this is a gas concentration cell, and for the gas concentration cell, pressure of hydrogen gas P1 is 600 torr, and P2 here, the right hand electrode, is 400 torr. And then you go for calculating your E naught, E cell. So E naught is 0 for hydrogen electrode. So E cell will be equal to either you write minus 0.0591 by 2 log of P2 by P1. It comes out to be 0.0052. So it says this value is positive. Then what all you have assumed that reduction is taking place at P2 is correct. So reduction, this is the reduction half cell and this is the oxidation half cell. Clear? Okay. So this much is there in the corrosion chapter, and the book PDF of corrosion has been shared with you on the WhatsApp group. Things are clear? So you should read from the PPT as well as, like, PPT is sufficient. If you don't get certain things in the PPT, you can go through the book PDF. Okay.
Have
So
you
today we will
shared this
stop
PPT?
here.
Have you shared this PPT?
You are not audible to me, like, but your sound is breaking.
Ma'am, he is asking, have you shared this PPT?
This PPT I have not shared. If you want, I can share this PPT also.
Do that, ma'am, please.
Please, ma'am.
Okay. So this PPT also can be shared. Okay, so now we have a class on Thursday. So Thursday we will try to complete two parts. One is crop synthesis, and the other part of it is your coordination chemistry. Friday we will complete your what is remaining, interaction of radiation with matter, and Saturday we will complete polymers. Okay, so that is how this weekend your syllabus for chemistry will get over. Then you are free to, like, by the time you are submitting 26th, you are submitting before 26th, you will submit your practical files. Okay, so then we can have a test. Test can be latest by 28th of February, Monday, next Monday. We can have test on this portion, right? Monday or Tuesday. Tuesday is a holiday, so test can be on Tuesday. That will be a better time uh, for the test, because that will be hardly for half an hour. So any day we can conduct test at